we start the deep dive 3. The title of the panel is Mitigating Risk of Battery Energy Storage Solution, Operation and Commissioning with Battery Analytics. We are more than wonderful to have Dr. Georg Angenent with us. He's the CTO and co-founder of Acure Battery Intelligence. Dr. Georg Angenent is a scientist and entrepreneur with experience in utility-scale battery energy storage solution. His research on testing, modeling, commissioning, and optimization of battery storage system has been published in international journals and at conference. Since 2020, he's the Chief Technology Officer at Acure Battery Technologies, developing advanced analytics software to help companies assess battery risk, ensure safety, and maximize asset value. With that being said, please, Georg, you can start your presentation. Thank you for that. Thank you for joining.
Yeah. Thank you very much for the kind introduction. Welcome to my presentation on batteries and especially grid-scale storage batteries. So within the presentation, I will show you 2 results of scientific papers, 4 common commissioning challenges where you must watch out for, and 2 deep dives into technical or into battery safety algorithms. So it won't get boring. All right. As we know, our mobility and energy future is built on batteries. And this is why we see more and more batteries. So we have electric vehicles on our street, and we use utility-scale storage systems to level load and demand. And especially in the utility-scale storage sector, we see rapid growth. So in Europe, we will commissioning 3.7 gigawatts of battery storage systems until the end of this year. And until 2030, 108 gigawatts of storage systems are required to reach climate targets. But with more and more batteries, we also see more and more batteries fail. This could be delays in the commissioning phase, but also failures in operation, such as underperformance or safety incidences. Here on the right-hand side, you see an example of the Victoria Big Battery fire in 2021. So this was a 450 megawatt hour battery energy storage system from Tesla, which caught fire during the initial installation phase. And as the PV magazine pointed out, this likely could be mitigated had the monitoring services not been switched off. So this is why we see a lot of delays in commissioning. And this is crucial because this leads, first of all, to loss of revenues for delayed commissioning. This could lead to fees for non-compliance with supplier contracts. And the risk is real because we already see that we have 8 gigawatt of commissioning delays in the US. But also in operation, we see problems. In operations could be underperformance or battery failures and fires, which cost companies billions in damages. And the worst thing is that people can lose trust in a key technology which is going to change our lives for better. So what can we do to mitigate these risks? First of all, we can improve the production quality. But on the other hand, we currently need to ramp up production at a lightning speed. So this means we need to produce more battery cells within shorter times, and on the same time focus on the production quality. So there's always a trade-off. So the second thing we can do is we can build resilient systems. So this means we can build battery storage systems where when one cell has an incident or failure, it does not propagate to the entire system. So and both of these solutions are really good, and we have to do them. But there's also a third option, advanced data analytics. And this is the one which I want to dive deeper within my presentation. All right, I've split my presentation in 2 parts. First of all, I will give you insights into data analytics in the commissioning phase, and then I will give you insights into data analytics in the operation. Let's start with data analytics in the commissioning phase. So the commissioning phase is the first critical step in the value chain of a battery. In this phase, all the responsibilities and risks are transferred from the contractor to the client. And additionally, substantial financial risks are linked to the commissioning phase. Because after, or if the commissioning is successful, a significant portion of the agreed upfront payments are transferred from the client to the contractor. However, as you can see on the right-hand side, or as you already know from the BESS curve, that the failure rates of systems are especially high in the beginning, in the early phase, and in the wear-out phase at the end. And this is why the commissioning phase is really, really critical. And also, we see a lot of time pressure during commissioning, because there's a huge incentive for fast commissioning due to high penalties for delays. We have already seen that some contractors need to pay $100,000 per week per week of delay. Another problem is that commissioning reports often lack of battery details. They are mostly focused on high-level functionalities such as hold point testing, black start capabilities, and integration with power plants, but not really detailed when it comes to batteries. And this leads to uncertainties regarding safety and performance. In the following, I want to show you a case study. So this is a case study from a US hybrid battery facility with over 100 megawatt hours of batteries. And this facility already had delays of several months during the commissioning. And as mentioned before, this led to significant amounts of missed revenues. So the IPP contracted a cure to help them within the commissioning phase. What we did is we did an analysis of the entire system, and we found out that there was a battery management system failure, which causing a faulty state estimation or faulty estimation of the state of charge. So what we then did is we triggered a targeted recalibration. So we worked together with the IPP on a recalibration program, and after we run this recalibration program, the system again reached full performance. Because for such a huge success, the IPP contracted a cure to continuously monitor the entire portfolio. So in the following, I will present you 4 typical technical challenges in the commissioning phase. And all these are based on real-life projects from our experience with over 3 gigawatt hours of connected battery assets. The 4 challenges I would like to present you are cell quality and connection issues, BMS failures, state of charge estimation errors, and water and heat damages. Let's start with the first challenge, cell quality and connection issues. So first of all, batteries have a substantial production spread. And this is what you see on the right-hand side. On the right-hand side, you see an aging test of over 100 identical battery cells, which we have aged under the exact same conditions. But even though these cells seem identical on day one, they developed a huge spread during their end of life. So this means that these batteries won't stay the same over time. And this is critical because the performance of a battery system is defined by its weakest link. So even if you have a lot of good cells, one bad cell could reduce the performance of the entire system. And also single cell failures in battery racks can lead to accelerated aging, system imbalances, or incidences. And this is also one thing which, or why even the best trained battery models are not perfect or not 100% accurate, because you cannot measure all the outliers. All right, and here's a case study how it looks in real life. This is the result of analysis which we have done for one of our customers, where we analyzed the internal resistance. And interestingly, this internal resistance is normally not evaluated during the normal commissioning phase. So what we find out is that the system integrator uses uses cells from different production batches, which results in different internal resistance. And even worse was that the cells which they used, with the cells from this third production batch which they used, were already liabilities before the battery storage system was officially commissioned. The second challenge I want to present you are battery management system failures. Battery management system failures can lead to downtimes. Yeah, for example, if the BMS falsely believe that the battery system already reached his operational limits. It also can lead to deep discharge, which causes or increases the risk of internal short circuits, or it can lead to overcharges, which increases the risk of thermal runaways. And on the right-hand side, again, you see a case study. So we found at one system that already during commissioning, deep discharge occurred due to parasitic loads and faulty active balancing. So this means for this system, the warranty was already voided during commissioning, and a safe operation could not be guaranteed after this. So this is why it's really, really important to check all the battery parameters during the commissioning phase. Third challenge, SOC errors and imbalanced regs. So especially for LFP battery systems, SOC errors are common. We have already seen errors of 20% or above. And these SOC errors can create balancing problems and imbalances. And additionally, also reduces the value of the asset, because if you cannot use the entire capacity of the asset due to BMS or SOC estimation errors, you cannot optimally trade your asset. And on the right-hand side, you again see a real-life example. So what we found there was a high SOC difference between different regs. And we were able to show that the actual spread was significantly lower, and it was really a BMS issue or BMS SOC estimation issue. So again, we worked on a recalibration, which solved the problem. The last challenge I want to dig deeper is water leakage and heat damage. So first of all, failures of cooling and fire suppression systems already started several fires. And this exactly was the case at the Victoria Big Battery fire I was shown in the beginning. But also what we have seen is that that we have leakages, water leakages. So the containers have water leakages and water was going into the battery containers. And this was a repeated problem for battery energy storage systems. And on the right-hand side, you again find a real-life example. So we found high temperature. Also, although the system was inactive. So on the right-hand side, you can see a temperature rise of over 60 degrees. And then we said, hey, how could this be? So what we find out is that the dehumidifier causes this temperature rise. So they had a leakage or water leakage in their container. So this is why the container was wet. And they tried, what they did is they dried the water with the dehumidifier. But the dehumidifier causes the temperature rises at the battery system of over 60 degrees. And of course, this is a big problem because after such temperature rises, the battery warranty is already violated. And these high temperatures can reduce battery performance and lead to irreversible damages. So it's not, it's not safe to run this battery. All right. So with this, yeah, you already get a good overview of 4 major challenges in the commissioning phase. So I've presented you cell quality and connection issues, BMS failures, state of charge estimation errors, and water heat damages. I showed you the issue and also the solution and the value add battery analytics can provide. Cool. With this, we come to the second part of my presentation, data analytics in operation. So again, I split it this part in 3 parts. First of all, I will show you the general working principle, and then I've brought you 2 examples, one of a resistance anomaly, and the second one is of an OCV anomaly. Good, let's start with the working principle and the collection and managing of data. So here you can see an overview of how field data works. So in generally, every battery cell is constantly supervised. So it's constantly, from every cell, constantly voltage, temperature, and current is measured by its BMS. Because as you probably all know, you're not allowed to deep discharge a battery cell or overcharge a battery cell. So this values then are transferred to the SCADA system, and the SCADA system then can transfer the data into the cloud, where all the cloud analytics algorithms can do it magic and provide the results in dashboard. And what we at Acure do is we provide the right-hand side. So what we do is we bring the already existing battery data into the cloud, and once there, we run our algorithms to find anomalies, to prevent incidences, and present these results in dashboard or via an API. And so the great thing is that no product modifications are needed, and only the already existing data are sufficient to provide additional values for customers. But why is it necessary? Why cannot do the BMS all this on its own? So when it comes to battery diagnostics or different algorithms for battery diagnostics, you always have a trade-off between robustness and accuracy of these algorithms. And when you design a BMS, you want to have algorithms which are really highly robust, because of course you have to shut down if you see an overvoltage. There cannot be some kind of estimation errors or so. So this is why in a BMS, often rule-based or logic-based algorithms are used, or partly empirical or data-driven algorithms. But again, if you want to use the full power of battery diagnostics, you also can use all the other diagnostic tools, and they can be used in the cloud. So the cloud can use more accurate but therefore less robust algorithms. So to recap, the BMS reacts to actually occurring situations, and the cloud diagnostic can, due to its higher accuracy, proactively handle anomalies and use forecasts. And this is already reality. We at Acure monitor already over 3 gigawatt hours of battery storage systems from a lot of different domains, electric mobility, energy storage systems. We have over 60 employees and offices in Germany and the US. And besides the commissioning support, we offer 3 products to our customers. First of all, the Safety Manager, which prevents safety incidences. Then we have the Performance Manager, which protects you from underperformance, and the Lifetime Manager, which increases the lifetime. And I want to dig a bit deeper in the following slides in the Safety Manager. So in general, our Safety Manager has over 20 indicators which are used to detect several safety critical states. And all these indicators are combined into one safety score, which then which then shows how safe a battery storage system is. And out of these over 20 algorithms, I want to present you two in the following. So first of all, is an algorithm to detect resistance anomalies. All right, if you calculate the internal resistance or impedance of a battery storage system, you will get such a graph, or you will see like something like this. And the only thing which you can directly see, it's really noisy. So you maybe have some temperature or SOC dependencies, maybe also some aging trends, definitively a lot of noise, and also maybe you can see some safety critical trends, but yeah, as mentioned before, really noisy. So let's apply the power of cloud analytics. Okay, we take an example of an electric vehicle. So this electric vehicle is driving around at different temperatures and different state of charges. And this is how a driving profile could look like. What we then do is we look into this driving profile and identify these points which are interesting for diagnostics. So in this case, we look into points where we really accurately can calculate the battery impedance. And then we get some points on our temperature and state of charge map. And if we do this not only for an average driver, but also add a cold location driver, and maybe a hot location driver and a commuter, we already get a much clearer picture. And if we do not only for 4 cars, but for maybe 10,000 of cars, then we get a really, really clear picture on the dependency of the battery impedance, temperature, and state of charge. And 10,000 batteries you also easily have within a utility scale or battery energy storage system. And this is how it looks like. Then you get kind of a map or correlation between impedance, temperature, and state of charge. And if you use this knowledge to clean your data, you can you can get rid of all the noise and really see the safety critical trends. All right, then let's go to the second example of OCV anomalies. So in general, the open circuit voltage curve is like the fingerprint of a battery. So it's the voltage of a battery as a function of the state of charge when no external current is flowing and all chemical reactions are relaxed. And what makes it interesting is that each battery has an individual OCV curve based on their inner state. And this is why it's really, really getting interesting. Because since you have an individual OCV curve for every battery, you really can see you can get a hold on what is going on within the battery. However, it's difficult to extract the OCV curve from operation. And why is it? Why is this? So what you measure when you measure the voltage of a battery, you only can measure the voltage of the poles, but inside the battery there's going a lot of different reactions, which I will show later, which all influences the measurement. Okay, all right. And here you also see once again an OCV curve. So it's basically the same same as here, only mirrored. So don't get confused. So this is an OCV curve and how it looks like when it gets discharged. And what had happened is when I discharge a battery, the first thing is, or as soon as I connect my load, you will see that the voltage drops due to the internal resistance. And also we see some other drops due to reactions and diffusion processes. And then we start discharge, or then we discharge our battery until we reach our discharge cutoff voltage. And you already can see that the measured voltage is way lower in the discharge phase compared to the open circuit voltage of battery. And for in a charging, or if we do charge, is completely the other way around. And after we stop discharging, the battery storage system again starts to relax. And and because of the resistance, reaction, and diffusion processes. And because the understanding of the relaxation of battery storage systems is so important in order to extract the OCV curve from the from field data, we did a lot of investigation into relaxation of battery storage systems. And what we will do is, or what we currently do, what's currently ongoing is, we will publish a paper on relaxation behavior together in cooperation with Mathieu Dubarry. And this paper, or with this paper, we will release a benchmark data set of relaxation patterns for commercial LFP and NMC 811 cells. And we hope that we can make a contribution to the scientific community to provide a training set for new relaxation models. Because as seen before, relaxation is crucial, or the understanding of relaxation is crucial for OCV extraction from field data. And this is why we will release this paper and the test data set so that the community has also the possibility to find new and even better relaxation models. So within this paper, we did an investigation of the relaxation of LFP cells and NMC cells, independency of time, C rate, DOD, and temperature. All right, and here's an example how it looks like in real. Again, this is an example from one of our customers. So what you see here is in green the average OCV cell, and the OCV curve from a 40 cell, and you clearly can see that that there was a big shift of the OCV curve, and this big shift triggered a safety alert from our algorithms, and then this module was exchanged before the error became critical. And when you want to know more about extraction of OCV curves from field data and increase your understanding of open circuit voltage curves, I just last week I wrote a blog article, so you can read it if you're interested. But so this example here was quite obvious. You see that there's a huge difference in the OCV curve. But what you also can do is you can, during operation, you constantly can track the OCV curve and how it changes. And this is what is shown on the right-hand side. So in the beginning, we had the blue OCV curve, and then it changes to the red one. And as you can see, these changes are quite small. But what you can do is you can use incremental capacity analyses and differential voltage analyses to characterize these changes. And then and how it looks like is shown on the right-hand side. So here you can much better see how the OCV curve changes over time. The next step, what you then can do is you can use mechanistical modeling to explain these changes. And here, for example, we found a typical indicator for loss of lithium inventory, and could detect loss of lithium inventory for this battery cell. And why is it relevant? Because loss of lithium inventory is a precursor for lithium plating. And also here, a post-mortem analysis revealed extensive plating within this battery within this battery cell. So this was also, again, quite a good example how cloud data analytics, the extraction of OCV curve, and the analysis of OCV curves with mechanistical modeling can help to prevent safety incidences. And because the understanding of loss of lithium inventory and also other mechanisms such as loss of active material is so important, we did a lot of investigation on it. And we published a paper again, together with Mathieu Debarry, to accurately or for accurate loss of lithium inventory and loss of active material estimation using the mechanistical modeling. What we find out in this paper was that most state-of-the-art mechanistical modelings are inaccurately regarding the LLI and LUM estimation. And within this paper, we propose to an update of the mechanistical models to accurately detect loss of lithium inventory and loss of active material. This paper is already published, so you can go online, download it, and read it if you're interested. All right, and because our safety algorithm or safety product is working so well, we are already recommended by 4 insurance companies as a risk reduction measurement. So this means if you want to insure your battery storage system and you use the IQ monitoring, you get better insurance fees or better insurance products because the insurance company says, okay, we see lower risk, you get warned before something happened. Good. With this I'm already at the end of my presentation. Thank you very much for your attention, and I'm looking forward to our discussion.
Great, Georg. Thank you for your very nice presentation. Yeah, there are several questions. If you think so, Georg, we can start with Quan Huing. It's the detection granular to individual cell level. This is the first question.
So once again, could you repeat?
Again, no problem. Yeah, the first question is from Quan Hui. Is the detection to individual cell level? How is the detection?
So yeah, we can. This mainly depends on the connection of the battery storage cells. So normally, if you have if you have 2 cells connected parallel and just one voltage measurement, of course you cannot go down to the individual cell level. But if you have an individual voltage measurement for each cell, then then you can go down to the cell level.
Great, thank you for that, Georg. Then, how do we determine a state of health and a state of safety?
Okay, cool. Yes, for starting with state of health. So for the state of health, we constantly do capacity estimations online. So this means we analyze the patterns. Therefore we search for cycles which are and then weight the capacity we see within the cycles with the DoD. With this we are able to determine the state of health during this operation. And the second question was regarding the state of safety. Therefore, I presented the safety score. So we have over 20 different algorithms which looks for different patterns which are safety critical. And if one of these algorithms or multiple of these algorithms sees some safety some issues, then our safety score will rise. And this is how you get at least a hold on the state of safety.
Great, thank you, Georg, for sharing that. Then the next question is, what are the input data passed to the cloud?
Okay, so what we use as input data is the current voltage and temperature measurements of these battery cells. And additionally, we also want to have some metadata, which means what is the capacity of the storage system, how are these cells connected, and for example, also when we do a lot of warranty tracking. So this means also we would like to know the warranty conditions in order to help our clients the best. But the only time series data we really need is current voltage temperature measurements of the battery storage systems, and everything else helps us to provide more value to our customers.
Great. They are also asking, about the cost. It definitely depends. It depends what are the data that you need to collect in. But yeah, if you have somehow, if you want to share something about what are the costs of an independent monitoring, if you have a ratio.
No, I won't share some costs, but it's surprisingly low.
Okay,
So,
that's nice.
and once again, the great thing is it's really only software based, so no product modifications are needed. We just use the data which is already available, and yeah, then do our analysis.
Great, Georg. Then also, Marianne is asking if this presentation could be shared by you, because joined a little late. That's one question. And last question from Kingo is, do you have any experience dealing with state of health estimation problems in balance to your OCV changing with age cell, especially when cells aging in different rate?
Yes. So first of all, can the presentation be shared? Sure, we can share the presentation. Second question was, did we see some SOH estimations errors or problems? And yes, of course, especially one of the biggest challenge I would say is that different state of health of battery cells also cause imbalances, and this always needs to take into account when to calculate the state of health of the entire system. So it's always a little bit easier to calculate the state of health of a single battery cell. But in the end, you're interested in how much capacity can I gain from my entire system, and therefore you need to take a lot of different things into account, which are of course the aging of all individual cells, but also things like SOC estimation errors, imbalances, and so therefore it's quite a big challenge.
Great. Then from Hassan, what is the frequency of data collection like?
It depends on our customers. So we have customers which send us data every second, but we also have customers which only send us data every 5 minutes. I would say so on average a minute or so. It's average time. But
great, thank you.
Maybe to add, so normally we with our customers we start working with the data which they already have, and then if we later in the process see we could deliver way more benefit if we have if we change the data logging, then we go together with the customers and see if it's possible and how we can do it.
Good. I think the next question is related to this last. What is the data rate that is necessary?
Data rate? What is meant by data rate?
Okay, that's it. Gerald, if you can, share that, what you mean for data rate. That's great. So far, many questions, Jörg. Very, very nice. And how you think we can manage to share the presentation?
I don't know. Maybe battery associates take care of it. Or yeah, I can send it to you.
That's good. So we manage. Okay, it's Gerald mentioned that it's a similar question from Hassan.
Okay.
I think we are coming to the end. And yeah, Georg, very, very nice presentation. Very many insightful information. And yeah, I take that with us that it doesn't cost too much, as you mentioned.
Yeah.
It doesn't cost too much. That is also from Gerard's questions, but it's also very, very highly relevant, no, to get safe and to get control of the cells and the batteries as you can measure all that. Yeah. Then thank you all to joining, and yeah, see you. I think now it comes networking till the US part till 5 o'clock.
Cool. Yeah. Okay. Thank you very much for all the questions.
Thank you much.
Discussion.
That's it.